All right, chemical reactions and chemical quantities. Since we're in Chem 1, I'm assuming that you've already gone over this at some point in the past, either in high school chemistry or in Chem 20. So some of this we'll just kind of be rushing through, and that's why. You may know that there's a thing called a greenhouse effect. So there are gases in the atmosphere that can allow sunlight through. They come in from space, and that sunlight can warm the Earth. It can also reflect off, and because it's lost some of its energy, it gets reabsorbed by the gases, gets transformed into more heat that gets reflected back into the Earth. So overall, there's a net capture of energy. And that balance between the incoming energy and the outgoing energy determines, in part, its average temperature. So in the last many years, scientists have measured an average 0.7 degrees Celsius rise in atmospheric temperature, and atmospheric CO2 levels have also risen. However, just because two things happen doesn't mean that they're related. So we want to know, are the two trends causal? Well, atmospheric carbon dioxide has been going up, global temperature has also been going up, and why are all the slides blank? One sec. Okay, we're back. We've got the slides again. So one of the places that CO2 comes from is combustion reactions with fossil fuels that we use to get energy. So burning things like methane, burning things like petroleum products. Another source of CO2 is volcanic action. And so how can we judge whether global warming, the average overall increase in temperature, is natural, just due to volcanic action, or based on the use of fossil fuels? So to understand a little bit more about this, we would have to know the chemical equations that describe fossil fuel combustion and how those relate to the amount of fossil fuel burned to the amount of carbon dioxide produced. So how do we relate how much fossil fuel we're burning to how much CO2 we're emitting into the atmosphere, and how does that compare against natural sources? So what we need to know about is chemical reactions. In a chemical reaction, chemicals react. Wow. So one or more substances are converted, changed, rearranged into one or more different chemical substances. So we're rearranging the atoms. We're not destroying the atoms. We're not doing nuclear chemistry. We're just rearranging the atoms, putting them into a new rearrangement, new organization, and that involves chemical changes. The atoms themselves are unchanged. So this would be like if you had an old Lego set that was lying around and you thought, hey, that's a fun old Lego set, but let's see if we can do something new and fun with it. You break the whole Lego set down and you build a new Lego set completely from that. That would be like a chemical reaction. All the pieces are still there, you've just changed the way that they're ordered. It's a little bit like anagrams as well. You're moving all the letters around, but you still are using the same letters. A combustion reaction is a particular type of chemical reaction. In a combustion reaction, a substance combines with oxygen in the form of O2 to form one or more oxygen-containing compounds, like CO2 and H2O. CO2 and H2O are common combustion products. There's also heat that's produced in combustion reactions. As we hopefully all know, if you burn something, heat's released, right? That's burning something is a combustion reaction. And so heat produced, the explosions that we make in our engines, lots of other things are involved in supplying our society's energy needs as well as getting around because of the way that we've structured our society. And so the way that we would represent this is with chemical equations. This is just shorthand for describing chemical reactions. Rather than writing whole long sentences, we simplify things down so that we can quickly and easily read what's going on with our chemistry knowledge. So we've got reactants on the left side. We've got products on the right. I'll often talk about these two interchangeably. So left and reactants, or right side and products. And in the middle, we've got an arrow, or sometimes we'll have a double-headed arrow. You might also see sometimes there's extra information around that arrow. We won't be doing that a whole lot. So these equations can provide some information about the reaction. What are we putting into the reaction? and what are we getting out of the reaction. We're not going to get really too much into the details of what's going on that arrow side. We're mostly just concerned with where are we starting and where are we ending. In organic chemistry, a lot of your focus would be on what's happening in that arrow. So we're getting the formulas, chemical formulas, usually molecular formulas or formula units. We're getting the states of the reactants and products. You should know all of these states, the abbreviations and their states. So following each of our reactants, we would have G, L, S, or AQ, depending on which state they're in. Aqueous just means that it's a water solution, so it's dissolved in water. And we can use the number of reactants, the number of products to do calculations, which we'll be getting to. So as one example, combustion of methane, this is what you would be doing at your gas stove at home if you have one. So in the combustion of methane, methane gas burns with oxygen, O2, to produce CO2 and H2O. And if we look closely at this equation, if we look at the parts that are pulled out below, we notice a problem. We've got a different number of oxygen atoms on the left side versus the oxygen atoms that we have on the right side, which means we've magically created one oxygen atom. And we know that we don't magically create oxygen atoms or any other type of atoms because of the law of conservation of mass. Not only that, but we also have the wrong number of hydrogen atoms. We've got 4 on the left, 2 on the right. And so the way that we've written our equation is false. It violates the law of conservation of mass. We're magically destroying hydrogen and creating oxygen. It doesn't work like that. And so what we need to do is balance our chemical equation. And to balance a chemical equation, we're going to change the numbers in front. We're going to change the coefficients on our chemical formulas. So for example, saying that we've got 2 oxygen molecules instead of just 1, and we're producing 2 water molecules instead of just 1. We are not going to be changing the subscripts. So subscripts are these dropped and following numbers. If we change those, then we would be changing the chemical reaction, and we don't want to do that. So we would adjust that until they are all equal. Another thing that we have to be able to do is properly count the number of atoms in a chemical formula. So there's a little bit of, I don't know if it's even algebra, there's some arithmetic at least, that we have to do to be able to balance chemical equations. So let's say that we're balancing the oxygen. We can see that on the left side, we've got 4 FeCO3 molecules. So 4 times 3 oxygens, which is 12. And we've got another 2 from the O2. So on the left side, we've got 12 plus 2, 14 oxygens. We also need to know how many do we have on the right side, how many do we have on the product side. We've got 2 Fe2O3s, so 2 times 3 oxygens, plus we've got 4 CO2s, so 4 times 2. So we've got 6 plus 8, we've got 14 oxygen atoms. So we need to be able to do these types of, I think they're relatively simple calculations. However, it's easy to screw these up, especially if we've got multiple polyatomic ion groups, then things get even more complicated. So we just need to make sure that we're being diligent about counting the number of each of the elements. So if we want to balance a chemical equation, we first need to write a skeletal equation. The skeletal equation is the bare bones, just the absolute minimum that you would need to say that this is the chemical reaction that's going on. So what are the reactants? What are the products? Not how many of each there are, just what are the reactants, what are the products, what are the chemicals involved? Oftentimes this will stem from or start from a word problem. So you'll be told in word form the names, and you'll have to come up with the chemical formulas. So this is where our nomenclature knowledge comes into play. And then we can balance the atoms that occur in more complex substances first. So usually if it's in one thing or multiple things on both sides, we would balance those first. And then once we're done with doing that, we'll balance the atoms that occur as free elements last. The reason that we do that is when we change the coefficient, we shift up or down the number of these free atoms, these free elements, it's not going to affect our count for anything else. So we can do those last, and it's not going to screw up our other counts. Sometimes it'll be fastest, it'll be easiest if we use fractions, coefficient fractions. And so to get rid of those coefficient fractions, we would multiply all of our coefficients by the same number. We should see some examples of this. And then last but not least, check and make sure that it's actually balanced. So we can do another count at the end. All right, so an example. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce, keywords, this is our arrow, solid silicon carbide and carbon monoxide gas. All right, so silicon carbide, we don't necessarily have the tools for that, but that's fine. So silicon dioxide is SiO2. We've got the di prefix, meaning that we're treating this like a molecular compound. It's a solid. We are also reacting with solid carbon, which is just C. And this is going on to produce solid silicon carbide, SiC, and carbon monoxide gas, CO, as gas. So that would be our bare bones, our skeleton, our skeletal equation. Then we would need to start balancing things. So on the left side, we've got silicon, we've got oxygen, we've got carbon. We have the same things on the right side. The first things that we would want to balance are things that occur in multiple things, more complex things. So we're going to leave carbon for last since carbon's by itself, so we can change that one up or down as much as we want. It's not going to affect anything else. So let's balance our oxygen first. For our oxygen, we've got 2 oxygens on the left side. We've got 1 oxygen on the right side. We can get our oxygens to balance by adding a coefficient of 2 on the right side in front of our CO. Now we've got 2 oxygens. The other thing that's in multiple things on both sides is our silicon. Our silicon, we've got 1 on the left side in our silicon dioxide. We've got 1 on the right side in our silicon carbide. So we didn't have to do anything there, nice and easy. And then the last thing that we've got to balance is our carbon. Currently we've got 1 carbon on the left side in our just lone carbon, and we've got 1 in our silicon carbide, and we've also got 2 in our carbon monoxide. So we've got 3 on the right side, we've only got 1 on the left side. We need to triple the amount of carbon we've got on the left side, so we add a coefficient of 3 in front of carbon, and now this should be balanced. Questions? Cool. Let's say that we want to write a balanced equation for the combustion of gaseous ethane, C2H6, which is a minority component of natural gas. So we've got gaseous ethane, C2H6. It's going to react with gaseous oxygen. Gaseous oxygen is O2, and this goes on to form, that signals our arrow. This goes on to form gaseous carbon dioxide, CO2, and gaseous water, H2O. So that would be our skeletal equation. and now we have to balance it by putting in coefficients. So starting off the balancing, we've got oxygen by itself. It's O2 because it's one of our diatomic or molecular elements. We've got carbon and hydrogen both in a compound on the left side, and they're individually in compounds on the right side. So let's start off balancing carbon. It probably doesn't really matter what you balance first. You can balance either carbon or hydrogen first. So for carbon, we've got a subscript of 2 in our C2H6, so we're going to have 2 of those. We currently have 1 carbon on the right side in our CO2. To get those to balance out, we need 2 CO2s on the right side to double our amount of carbons. Now we've got an equal amount of carbons on both sides, so we can move on to our hydrogens. For our hydrogens, we've got 6 on the left side because of the subscript of 6 on our hydrogen, and on the right side we've got 2. To turn 2 into 6, since we've got 2 hydrogens in every H2O, if we multiply that by 3, that'll give us 6 total hydrogens. Now we can balance our oxygen. So oxygen's the last thing that we've got. We currently just have 1 O2 on the left side. We now need to count up the number of oxygens we have on the right side. And this is where we're going to run into coefficients. So we've got coefficient of 2 on our CO2, so we've got 4 oxygens. And we've got 3 H2Os with 1 oxygen each. So we've got 4 plus 3 for a total of 7 oxygens on the right side. What can we multiply 2 by to get 7? Seven halves or 3.5. So if we multiply this by 7 over 2, then we would get 7. And this is going to make some of you uncomfortable, perhaps. We can't have 7 halves of oxygen molecules O2. That's true. However, this is balanced. But since we can't have half of an O2 molecule, we need to change all of our coefficients. So one of the things that you could do instead of doing it this way is you could say, well, we have to multiply everything. We have to do something with our oxygen. Let's just keep multiplying stuff until it works out. And that might take you a while, depending on how many things you have. Or, since we've got it balanced, we can get rid of that 7 halves by multiplying the entire thing by 2. So we're going to take our entire chemical equation and multiply all of the coefficients by 2. That'll get rid of the 7 halves. It'll turn into 7. All of our other coefficients will change, but since we're multiplying everything by the same number, it'll still be balanced. So we'll have 2 C2H6, which is a gas, plus 7 O2, also a gas, going to 4 CO2, gas, plus 6 H2O, gas. And then if we wanted to, if we didn't trust ourselves, or if we just weren't sure, I trust myself, I'm very sure, we could go back and check and make sure that it's balanced. Just do one last run through. You might be able to do that in your head. I'm going to skip it because I want to. Questions about that? I think for this class, it's typically going to be combustion reactions where we'll end up with weird numbers of oxygens. It's where it shows up the most. We can also balance chemical equations with ionic compounds that have polyatomic ions. So for example, write a balanced chemical equation for the reaction between aqueous lead-2 nitrate, aqueous potassium chloride to form, that's our arrow, solid lead-2 chloride and aqueous potassium nitrate. What fun. What a joy. So this is a different type of balancing problem. We're also dealing with ionic compounds, and so we get to go through all of that fun. I'm just going to assume that we've all got the nomenclature mastered, even though that's probably not true. So our lead 2 nitrate means that we've got 2 nitrate groups, because nitrate is NO3 minus, and it's aqueous. We've also got potassium chloride. Potassium's a 1 plus, chloride's a 1 minus, so they go together in a 1-to-1 ratio, and that's also aqueous. Then we've got solid lead 2 chloride. Lead's a 2 plus, chloride's a 1 minus, and so it goes together in a 2-to-1 ratio. 2 chlorines for 1 lead. This is a solid. And we've also got aqueous potassium nitrate. Potassium's a 1 plus, nitrate's a 1 minus, and so those go together in a 1-to-1 ratio. So let's take a moment, now that we've got our skeletal equation, and let's find which things exist in one or more compounds on both sides. Well, let's take a look at our lead. We've got lead in our lead 2 nitrate. We've also got lead in our lead 2 chloride. Okay. We've got nitrate in our lead 2 nitrate. We've also got nitrate in our potassium nitrate. Okay. We've got potassium in our potassium chloride. It's also in our potassium nitrate. We've got chloride in our potassium chloride and also in our lead 2 chloride. So what do we start with? We start with, for most of these, I just say start with anything that's different. It doesn't really matter. This strategy does not always work out nicely, but it often works out nicely. So the strategy is pick something that's different. I usually pick the first thing from the left. That's different. And we're going to keep our polyatomic groups together because they're going to stay together in chemical reactions. We're not going to be breaking them up in this class, as far as I remember. So we can keep that together as one whole group. How many nitrates do we have on the left side? We've got 2. We've only got 1 nitrate on the right side in our KNO3. So to get those numbers to be equal, we add a coefficient of 2 in front of our potassium nitrate. When we add this 2 in front of potassium nitrate, what changes other than the nitrate? The other thing that changes is the potassium. So we're going to balance potassium next. So we're laying down, we're causing chaos, and we're following our train of chaos that we're producing. So we've got now 2 potassiums on the right side. We currently have 1 potassium on the left side in our KCl. To get that to balance, add a coefficient of 2. Now we've got 2 potassiums on both sides. When we change the potassium on the left side, what else do we change? Chlorine. The chlorine also changes, so let's balance chlorine next. So Cl, we've got 2 on the left side, and we've got, oh, look at that, 2 on the right side. So that's already balanced. And then we just check our last thing, and our last thing in this case is lead. We've got 1 lead, 1 Pb on both sides. So this is all balanced up. So the strategy, pick something that's different, balance it. Whatever the coefficient that you added, you're going to balance the other thing that's in there because you just changed that. And just keep doing that pattern. It doesn't always work, but it will often work. And that's just for this type of what's called a double displacement reaction. So if everything's in one thing on both sides, then we can use this method. Okay, so beyond balancing things, we'll be using our balanced chemical equations to do stuff. And that stuff is stoichiometry. Stoichiometry is a big fancy word that basically just means we're talking about the ratio of the components. How many things do we put in to how many things do we get out, or how many of one thing that we put in to the other thing that we put in. We're just looking at what's the ratio of the different components. We're looking at the coefficients. So the balanced chemical equation for fuel combustion reactions provides a relationship between the fossil fuel that's burned, in this case octane as our representative fossil fuel, and the amount of oxygen we use, the amount of CO2 we produce, the amount of H2O that we produce. So stoichiometry is just using the ratio of chemicals. That's all we're doing with this. And our coefficients in this chemical reaction specify relative amounts in moles or atoms or molecules. We're usually going to be talking in moles of each of the substances in the reaction. So for example, 2 moles C8H18 will turn into 16 moles of CO2. So we can use that as a conversion factor. So if we were starting with moles of C8H18, our octane, and going to CO2, our conversion factor would be 16 moles CO2 over 2 moles C8H18. And you can make as many of these conversion factors as you want. There's usually a lot, especially if you've got multiple chemicals on both sides. And so this is all that we're talking about when we're talking about stoichiometry. How do we convert from one chemical to another using a balanced chemical equation? Or put another way, the study of the numerical relationship between chemical quantities in a chemical reaction. I just usually talk about it as ratios. How many things in, how many things out. We can analogize this with pizza. Pizza time. So the number of pizzas you can make depends on the amount of ingredients you use. So a balanced chemical equation is basically a recipe. It's a recipe for doing a chemical reaction, just like a recipe for pizza where you've got a crust, you've got tomato sauce, you've got cups of cheese, and you produce a pizza. It's just like a recipe. It's the chemical version of a recipe. And so we can express this relationship mathematically: 1 crust to 1 sauce, or 5 ounces of sauce, to 2 cups of cheese to 1 pizza. So if we've got 10 cups of cheese, how many pizzas could we make from that? Well, we would pull out the 2 things that are relevant: cheese and pizza. All right, 2 cups of cheese in equals 1 pizza out. So 10 cups of cheese. It's a lot of smiling. And our ratio, we produce 1 pizza for every 2 cups of cheese that we put in. So we're canceling our units of cheese, and now we are talking about the number of pizzas we can create. So 10 divided by 2, turns out we can make 5 pizzas. We are making an assumption when we do that calculation. Does anyone know what one of those assumptions is? We have enough of the rest of the ingredients. We're assuming that we've got at least 5 pizza crusts. We're assuming that we have at least the relevant amount of tomato sauce. That's not necessarily true. Those are assumptions that we're making, and those might not be true. But if cheese was the thing that we were worried about, we just for some reason don't have a lot of cheese, or we've just got a ton of pizza crusts and tomato sauce in the freezer or in the cupboard, we can do this calculation. With molecules, we're doing a similar thing, but we're doing mole to mole instead of cups of cheese to pizza. So we can use the ratios of the coefficients to convert chemicals. So using our octane from before, if we burn 22 moles of C8H18, how many moles of CO2 form? So the 2 chemicals that we're interested in are octane, C8H18, so we'll underline that, and CO2, which is 16 CO2. So those are the 2 things that we're going to be using to make our conversion factor. Since we're starting with 22.0 moles of octane, we're going to put the octane part on the bottom so that they cancel. We're going to put the CO2 part on top. And we could put in, if you wanted to, you could put moles in on the top and the bottom. I usually just omit it. So what we'd put into our calculator is 22 divided by 2 times 16. I don't know what 16 times 11 is off the top of my head, so calculator gets out. Great. Relatively simple. 176 moles CO2. Any questions about doing that calculation? What we're doing there? How did I know that the reaction was balanced? We have to have a balanced reaction to be able to use the coefficients. So how did I know that it was balanced? I didn't. I just assumed that it was, and the reason that I assumed that it was is because it's got coefficients. So if the reaction has coefficients already, generally that means you can assume that it's balanced. If there's no coefficients at all, you definitely want to check. However, it's always safe to just go ahead and check it. Just real quick, do the math, figure out you've got the same number of things on the left and the right. But if the reaction has coefficients in there, that usually means that it's balanced. So doing mole-to-mole conversions, that's kind of our bread and butter for stoichiometry. We are more likely going to be doing mass-to-mass conversions. So the step that we were just doing is this middle step. This is what we do in stoichiometry. So that's what we were doing on the previous slide. And we can't really just measure stuff directly in moles most of the time. So oftentimes we're going to be starting with a mass of a compound, and we'll be interested in measuring a mass of a compound at the end, or predicting the amount of mass that we would produce at the end. And so we have to add on these extra steps where we go from mass to moles, and at the end from moles to mass. Who knows what we're going to be using to move between mass in grams and moles in moles? Any ideas? Molar mass. Exactly. So we need molar mass for chemical A. So we'll have molar mass A, and at the end we'll have molar mass B. So ideally, we're pretty quick at calculating molar masses. If you can calculate it without even writing anything out, you just throw it all in your calculator, awesome. I don't expect you to be there, but being good and being quick at calculating molar masses can save you some decent amount of time. All right, for example, US DOE, Department of Energy, says the world burned 3.3 times 10 to the 10 barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15 grams of gasoline. We'll just assume that that's all octane, even though it's not. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. So assuming all of that mass is octane, how much CO2 was produced? So our general stoichiometry solution map, in this case we're starting with grams, C8H18. To use our balanced chemical equation, we need to get to moles. So we're going to have to convert this to moles of the same chemical. And then we can convert to moles of CO2. using our balanced chemical equation, using our ratio. From moles of CO2, we can convert to grams of CO2. And we'll need the molar masses of both our octane and our CO2. And those masses are 114.232 and 44.009. So starting with our very large number, 3.7 times 10 to the 15 grams C8H18, we need to use our molar mass to convert to moles. So we need to divide the grams and the number part are paired. Those on the bottom, the moles part flips to the top. So dividing by our molar mass to get to moles. Grams cancel. And then we use our balanced chemical equation and our ratio of the two things we care about, the C8H18, the octane we're starting with, and the CO2 that we're going to. Since we're going to CO2, the CO2 part goes on the top. The thing that we have, the octane, goes on the bottom. This lets us cancel chemical units. So we're canceling our C8H18. We're now in units of moles of CO2. And then to get back to grams, we multiply by our molar mass of the CO2. So we're going to multiply everything that's on the top, the 3.7 times 10 to the 15, multiply that by 16, multiply that by 44.009, divide by 114.232, and also divide by 2. Questions? Yeah.
I'm just a little confused on like how they phrased it, why they said 3.7 something of gasoline. I would just like, if I read that, I would just think like automatically like to use oxygen as the molar mass going into it. But I'm just like.
Okay. Oxygen is not gasoline, so that would be one way to figure it out. So octane is usually, it's not the only thing, but like that's one of the things that's referred to in like the fuel number when you go to the gas pump. It's like 87, 89, 91.
Sorry, I just misread it.
Yeah, no worries. Other questions? All right, so this would be 1.1, the next number is 4, we would round that down, times 10 to the 16 grams of CO2. All right, so comparing that petroleum combustion number that we got on the previous slide, petroleum combustion in that year was about 1.1 times 10 to the 16 grams of CO2 per year. Volcanoes produce about 2 times 10 to the 14 grams of CO2 per year. So how much more CO2 are we producing than volcanoes, for example? If we divide the amounts, that will give us an idea of the relative size. So that number we just got divided by 2 times 10 to the 14, it's about 57 times more CO2. So if we set our petroleum combustion, CO2 production, to 100%, volcanoes would be somewhere like 2%, a little less than 2%. So that's a pretty decent argument that it's our CO2 production and not volcanoes that's kind of screwing up the atmosphere and the global temperature. All right, some more examples. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, according to the following reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing given amount of magnesium hydroxide? What are we starting with? What's our given? Yeah, we are given 3.26 grams of magnesium hydroxide. And what are we finding? Yeah, we're finding mass of HCl in grams. We know that's what we're finding, partly because it follows our question word. So this is another question that's written sort of backwards. It's just a different way of writing a question. So the two things that we care about, we're starting with magnesium hydroxide, we're going to HCl. So we want to underline both of those things in our presumably balanced chemical equation. It's got coefficients already. We're going to pull those two things out to make our stoichiometry, to make our ratio. So our solution map is going to look very similar, just with different chemicals, to what we did previously. Grams to moles to different chemical, in this case HCl, and then to grams of HCl. So that's what we're doing in this problem. That's our solution map. It's very common that our stoichiometry solution maps are going to be grams to moles to moles to grams. So that's an order that you can kind of roughly memorize. It won't always work, but it'll work a lot. And we're going to need molar masses. Fun. 2 molar masses. And we're also going to need our stoichiometry ratio. And the ratio is just what I underlined. So pulling out the coefficients for both of those chemicals. So let's get our molar masses, 24.31 plus 2 times the molar mass of hydrogen plus 2 times the mass of oxygen. (58.324 grams per mole), 35.45 for chlorine plus 1.008 for the hydrogen. Our molar mass is 36.458, roughly grams per mole. I'm just speeding through it to save us time. All right, and then starting with our 3.26 grams magnesium hydroxide, we're going to divide by our molar mass, just like we did before. Grams cancels grams. And now we have moles of magnesium hydroxide. We need to convert that to HCl. So we take the two things we care about, the 2 HCl, we put that on the top, we put the MgOH2 on the bottom. Magnesium hydroxide cancels. And then to get us back to grams, we multiply by our molar mass. So the grams is on top, the moles would be then on the bottom. And moles cancel. We'd be left with grams HCl, since those are the units that are left over. it's about 4.08 grams of HCl after we round. The other nice thing about my favorite calculator, since I calculated both of those molar masses just like right before doing this, you just press up, enter, up a couple times, enter, and pull out those molar masses, and then you don't have to punch them in, which is kind of nice. Questions? Cool, we're cruising. We're cruising so much I'm skipping an example. I can do it for you later if you want. All right, going back to that assumption that we made, because sometimes when you assume, certain things happen. So let's say that we are making pizzas again. We've got 4 crusts, 10 cups of cheese, 15 ounces of tomato sauce. How many pizzas can we make? We can make 3 pizzas. Why can we make 3 pizzas? Because that's the smallest amount of pizzas that we can make with each of our ingredients. So for our crusts, 4 crusts, it takes 1 crust to make a pizza. So we can make 4 pizzas from our crusts. We've got enough crusts that we could potentially make 4 pizzas. Again, the assumption that we're making when we do that calculation, we've got enough cheese, we've got enough sauce. But we don't know if that assumption's true, so let's look at our cheese. We looked at our cheese before. Cheese, it's 2 cups cheese to turn into 1 pizza. So we can make 5 pizzas from the amount of cheese that we can have. We have enough cheese to make 5 pizzas. And then the last thing that we would need to check is our last ingredient. We've got 15 ounces tomato sauce. It takes 5 ounces of tomato sauce to make 1 pizza. And so based on our tomato sauce, we can make a total of 3 pizzas. So that's the actual amount that we can make. We wouldn't be able to make 4 pizzas or 5 pizzas because we would run out of sauce. And a sauceless pizza just doesn't sound very good. So 3 pizzas is the max amount we can make. So it's just based on what's the smallest number that we can make based on our ingredients. Turns out 3. So we've got enough crust for 4 pizzas, enough cheese for 5 pizzas, but only enough tomato sauce for 3 pizzas. So our limiting reactant, or our limiting ingredient in this case, is tomato sauce. This is the one that runs out first. It limits the amount we can make. So if we, for some reason, needed to make 4 or 5 pizzas, we'd have to do a grocery run, get some more tomato sauce, or ask a neighbor, and possibly also get another crust, depending on how many more pizzas we wanted. So our tomato sauce is our limiting reactant or limiting reagent. That's the reactant that makes the least amount of product. It's the one that runs out first. And then the maximum number of pizzas that we can make is our theoretical yield. This is the amount that's made from the limiting reactant. We're only as strong as our weakest link, and our weakest link is pizza sauce. What this looks like in chemical reactions is a lot of grams to moles to moles to grams. We get to do one for each of our reactants. The good news is we're reusing the same product, so we don't have to calculate lots and lots of molar masses, just lots of molar masses. So if we have multiple reactants, it's likely, it's almost inevitable, that one of the reactants will be used up before the others. And oftentimes, we design our synthesis, we design our reactions so that one of the ingredients runs out first. We want to know which ingredient is going to run out first, so we'll limit the amount of that one, and we'll use an excess of the other one. When that one reactant's used up, our reaction stops, no more product is made. And that's our limiting reactant. Reactants that are not consumed are in excess, just meaning that we have extra. Again, this is usually designed in. It's often because we've got one reactant that's especially hard to work with. We don't want to try to remove it from our reaction mixture at the end. It's really expensive. Sometimes chemicals can be thousands of dollars a gram. So we want to make sure that we're getting our money's worth, and we would just use an excess of our cheaper reactants so that we make sure that we use it up, or other ideas like that. Okay, the amount of product that we make in the chemical reaction, like we go and make the pizzas, the amount that we get out, that's our actual yield. The amount that we make during the reaction. Oftentimes, almost all the time, at least in chemistry, things do not go perfect. We spill a little bit, some of it evaporates, we get some pollutants, we didn't quite use enough of our reactant. There's a billion things that could get in the way of us producing our theoretical yield. In the case of baking or making recipes, like our pizzas, maybe we burn a pizza, we've got one of our pizzas set out on their countertop, and our dog decides that that's the day that he wants to be naughty, and he goes up and grabs the pizza, and we say, well, we can't eat that pizza anymore because the dog had it. And so in reality, even though we can't make 3 pizzas, we only make 2 pizzas. 2 safe for human consumption, and our dog ate the other one. So we can calculate our actual yields, in this case would be the 2 pizzas. We can calculate percent yield. A percent yield lets us know the efficiency of the reaction. How many pizzas did we actually get out? By calculating the percentage of the theoretical that we could actually make. So we take our actual yield, we divide it by our theoretical yield, and since it's a percent reaction, or a percent equation, we multiply by 100%. You cannot calculate an actual yield. You can only find the actual yield by doing the experiment, or like if it's on an exam, you would have to be told this is the amount that was actually made. You can calculate a theoretical yield. The reason that you might calculate something like a percent yield, for example, if you're working in like a restaurant or something, or fast food, you need to know how many of the product that you can actually make, because you're going to burn some, you're going to drop some of it's maybe going to go bad, so you have to figure out some of this stuff like this. You wouldn't necessarily calculate a percent yield. In chemistry, it's pretty frequent that your percent yield might be 50% or lower, depending on how good the reaction is. So if I need to make 5 grams of product, and I've only got a 50% yield, I need to plan for twice the amount. I need to put in enough reactants to make 10 grams, and then I'll hopefully get the 5 grams out that I need. So percent yield is often published so that people know, hey, here's how much we were actually able to get when we did it, when we were working up writing this paper. And then other people can go and try it, and oh, I got a similar percent yield, so that means I did it about the same way that they did. Or oh, I got 20% less yield than the people in the paper did. I must be doing something wrong. Let's look for where that could have been. So that's the reason for using percent yield, and here's a big summary of limiting reactant and yield. Questions about all the fun we're having? Okay. So let's apply some of these concepts to a chemical reaction. Recall the balanced chemical equation for the combustion of methane. So methane's our CH4, reacts with two O2s, we get a CO2 and two H2Os. So this equation implies that for every one molecule of CH4 that we put in, it reacts with 2 molecules of O2. Let's say that we've got 5 molecules of CH4 and 8 molecules of O2. Which one is our limiting reactant? We'd have to go and do some calculations. So first we can calculate the number of CO2 molecules that we can make from CH4. CO2 would be one of our products, the one that we care about in this case. So based on our methane, we've got 1 methane in equals 1 CO2 out, 1-to-1 ratio, so we could produce 5 CO2 molecules based on the amount of methane that we have. Okay, so we figured out for our CH4, our methane, what's our yield, our theoretical yield. We would do the same thing then for our other reactant. So looking at our 8 O2 molecules, our ratio is 2 O2 molecules in equals 1 CO2 out. So 8 divided by 2, we would be able to produce 4 CO2 molecules. Again, we're looking at the same product. 4 is less than 5, of course. So 4 CO2 molecules for product is the smaller amount. So oxygen produces the least amount. It's the limiting reactant. Our methane, in this case, would be in excess, which is not ideal. And then 4 CO2 molecules is our theoretical yield. How much the limiting reactant makes. Now there is a shortcut. It's a really small shortcut. Some of you might want to do it, others of you might not bother. You don't technically have to go all the way to the product. You don't have to, like if we're going to end in grams, you don't have to go all the way to grams of the product right away. You can go to moles of the product and see which one makes the smaller number of moles, and then just go to grams of product from that one. That's an option. It saves you one step. Very chemistry to just save one step. So I'll point that out, I think, when we get to one. Let's say that we do the Haber-Bosch reaction. We do nitrogen and hydrogen gas. We react those together and it forms ammonia based on this reaction below. A flask containing this mixture of reactants on the left goes on to react. Which of these on the right represents our end state, the final product of all of this reaction going on? How would we calculate such a thing? It's not B. So the way that we would calculate this is we'd want to figure out how much of our reactants do we have. Our H2 is the white. We've got 8. We've got a group of 4 up here. We've got a group of 4 down here. So we've got 8 H2 molecules, and we've also got 2 N2 molecules. When these react, how many NH3 can we make from these number of molecules? our N2, we would put in 2NH3 over N2, our little stoichiometry part. So 1N2 in equals 2NH3 out. So we would be able to make 4NH3. What about for our H2? We put in 3H2 and we would get out 2NH3. 2NH3 over 3H2. We'd be able to make 2. Remainder 2 NH3. So we'd be able to make 2 NH2. That would use up 6 of our H2, and then we'd have 2 left over. So we're looking for the case, sorry, not 2. 2 batches. 4 NH3. With a remainder of 2 of our H2 left over. So we're looking for the one that would produce 4 NH3, and then we would still have the 2 H2 that's left over. So that would give us C. Our limiting reactant for this reaction would be our N2, and the H2 would be in excess. When we're using initial quantities in masses, we typically do the same front end or the same back end. We would do grams to moles of our one reactant to moles of our product, and then from moles of the product, we would go to grams of the product. So this is what I was talking about, one of the things I was talking about, where you can just calculate moles from each of the reactants and then pick the smaller amount and use that to go on to grams. So we would go from grams to moles for one reactant to moles of the product. We would stop. We would go from grams to moles of the product, and we would stop. Then we would look at, okay, which of our two numbers of moles is smaller? That's going to be the amount that we can actually make, and then let's only do the calculation from there, going to grams of the product. Let's look at an example of that. So we've got a reaction mixture. We've got some grams of magnesium. We've got some grams of O2. What is the limiting reactant, and what's the theoretical yield? And then as a second part, we can do a percent yield calculation. So the first part, we want to figure out how much product we can make with each of our reactants. So doing some parallel calculations, 42.5 grams magnesium, 33.8 grams of oxygen, O2. We need to figure out how many moles of each of our reactants we have, since our reactions use moles or molecules, not grams. They're not a mass-based, they're number-based. So number of magnesium molecules. We do the same thing for our O2. So we divide by our molar mass. And we could get a number out. Let's do that. I know some people prefer to do every step separately. So we get 1.748 ... moles mg. And for our oxygen, 1.056 ... moles O2. Then we need to see how much product can we make, because we use them in different amounts, right? The ratio to the products is not the same. So for our magnesium, it's 2 in, 2 magnesium in equals 2 magnesium oxide out. So 2 MgO over 2 Mg, the 2's cancel, the magnesium cancels, so it's just the same number. So based on our starting amount of magnesium, we can make a maximum of 1.748 ... moles of magnesium oxide. We need to also calculate the same amount for starting with our oxygen. So we're going to do same idea here. Our O2 to our MgO. This time we have a 2-to-1 ratio. So 2 magnesium oxide over 1 O2. The O2's cancel. We multiply that 1.05 and change by 2. We can make a little more than 2 moles of product. Which one of these is going to run out first? Our magnesium or our oxygen? Which one gets used up first? Which one makes the least amount, the smaller amount? Magnesium, right? It's got the smaller yield. So we're going to continue the calculation with this amount, because the other one we've got extra. So we take our moles of MgO, and now we can calculate the grams of magnesium oxide. We'll need a molar mass, so 24.31 plus 15 with 3 nines, 40.309 grams per mole. The moles cancel. Go grab that number. We would be able to make a maximum of 70.5 grams of MgO. Okay, so what is our limiting reactant? Magnesium. Magnesium is our limiting reactant, just based on the numbers that we were given. Limiting reactant is magnesium. The 70.5 grams is our theoretical yield. We can then calculate percent yield. Percent yield is actual yield. We were told that's 55.9 grams divided by theoretical yield, 70.47 and change grams, times 100%. Grams cancel. That's not the grams, that's the grams. And our percent yield is right around 79.3%, which is pretty good. So we made about 80% of what we could have if everything went absolutely perfect, which it never does. How many examples do we have? All right, I'm going to skip some of these examples, but I'd be happy to show them to you later if you want. And we're going to get on with some reaction types. So combustion reactions we've talked about a little bit. Combustion reactions are characterized by the reaction with oxygen. Reaction with O2 forms usually CO2 and H2O, not always, and also produces heat. That's a big part of the reason why we do combustion reactions and have historically done combustion reactions, is for heat. If you've got compounds containing carbon, hydrogen, and oxygen, the products of complete combustion are always carbon dioxide and water. So whatever sort of thing with C, H, and O you want to put in here, you can put in a sugar, you could put in a functionalized hydrocarbon, you can put in just a regular hydrocarbon, react it with O2, and you're going to get out CO2 and H2O, assuming that it goes to complete combustion, which we'll probably always assume for the class. So what that might look like, let's say that we're burning ethanol, C2H5OH. Write a balanced equation for the complete combustion of liquid C2H5OH. This is carbon, hydrogen, and oxygen only, and so we know that our products are going to be CO2 and H2O. And part of our definition for a combustion reaction, we're reacting with O2. Our products are always going to be CO2 and H2O since we have only carbon, hydrogen, and oxygen. So this would be the part you would have to memorize. You'd have to know that we're reacting with oxygen, O2. You'd have to know that we're producing CO2 and that we're producing H2O because our reactant has carbon, hydrogen, and oxygen only. The balancing part, we would just balance it like normal. For something like this where you've got the OH at the end, you might want to shove that H in with your other H's just so that you don't accidentally miss it. So that's the skeletal reaction. We also have reactions with, question?
So basically all compounds contain only carbon, hydrogen, and oxygen. The only products are always going to be carbon dioxide and water.
Yes, it's always carbon dioxide and water, assuming complete combustion. If it doesn't burn all the way, that's when you get like
And no other products.
other stuff. Correct, just those two, and heat. Okay, our alkali metals react vigorously. Alkali metals are very reactive metals, and they can react with halogens, which we're using X here to represent a halogen. So like chlorine, fluorine, bromine, iodine, acetine, etc. We would have, all of these are diatomic or molecular elements. And so that's why we've got the subscript of 2 here. So 2 of any of our alkali metals, like sodium, is going to produce an ionic compound made of the 2. And it'll also produce heat. It might produce sparks depending on how reactive it is. There's a fun video. I think it's fun. I think it's by the Royal Society of Chemistry. They react cesium metal, the most reactive alkali metal, with fluorine gas, just F by itself, I think, which is a very tricky reaction because chemists hate working with fluorine. It's super reactive, and it makes quite a fun reaction. It's like a 10-minute video, I think. Maybe it's shorter. Alkali metals can also react with water. So almost our last slide. It's our last slide, basically. Alkali metals can also react with water to form a dissolved alkali metal ion, hydroxide ion, and hydrogen gas. So they also dissolve in water. So examples, lithium reacts a little bit, sodium reacts more, potassium reacts quite vigorously, and the further that you go down all the way to cesium, the more vigorously it reacts. And this produces the alkali metal plus the hydroxide ion, and then the leftover H's, leftover hydrogens, go on to form hydrogen gas, which can also ignite. Questions? Okay, we did it barely, sort of. That's chapter 4.